In this video, we'll be talking about impedance changes and how data is actually evaluated in terms of impedance changes. So if you recall from looking at impedance plane diagrams from your study books and your readings, you can probably remember that inductive reactance is usually shown on the vertical axis and resistance on the horizontal axis. And the liftoff line is always going down at this angle. But what you do during actual data evaluation is, rather than keep that impedance plane like it shows in the book, what we do is we change that liftoff line to occur more horizontal. Okay, that's the first thing. We set noise horizontal. Now, as I take my cursor and scroll up through the data, first of all, right there, that's probe wobble. My impedance is changing just with probe wobble, because anything that changes the coil properties is changing impedance, whether that's fill factor, lift off, dents, bulges, flaws, deposits on the outside of the tube support plate. Anything that the probe sees is changing test coil impedance. And when I move over a flaw, that flaw is taking, actually when I load the coil with the test material, that's taking energy away from the coil, and it lowers inductive reactance and lowers impedance. But when I scan over a crack, or in this case, a flat bottom hole, that reduces the eddy currents flowing in the material because they're disrupted. And that gives energy and current back to the test coil, which raises test coil impedance, because the more current that's flowing in the coil, the more opposition there has to be to oppose it. So if a flaw gives energy back to the coil, that increases test coil impedance because there's more current flowing in the coil. Now, as I scroll up to a deeper flaw from the OD, we'll notice that my inductive reactance is going up more towards the air value from an unloaded coil. Then I get a little deeper flaw, our phase changes, our resistance changes, it's going down. And then the very last one we see is the 100% whole signal. So that has a different impedance value because the resistance and the inductive reactance of the coil have changed. Now I can guarantee it, if you walk into a room full of data evaluators and they're analyzing data from, for example, a heat exchanger inspection where they're using inside bobbin probes to examine the tubes, you are not going to hear them talking about impedance and inductive reactance and resistance. If you are, I'd be very surprised, because that would be rare. Because what you're really watching for when you evaluate data are changes to signal phase and amplitude. I think one of the best traits that you could have to be a really good data analyst is to have a good memory and to be able to recognize patterns. Now I'm going to show you what I mean. Rather than just look at this one absolute signal, let's configure the screen to show multi-frequencies. Now I'm going to put 4 different differential signals on the screen. 5. And then here on the lower right, I'm going to put 7. Okay, so the first thing I'm going to do is confirm that I've got a calibration that's fairly close to being right. And I can see that my lowest frequency, channel 7, I actually set using a support plate, so don't pay attention to that. But let me just go and adjust these. I'm going to adjust the null points just a tad. Let's see, configure. There's a 100% signal. So I'm going to take the channel 1 and put it there. I'm going to adjust the span a little bit. And I want all of these channels to have the 100% flaw calibrated about the same phase and the same amplitude. Make that one a little bit bigger. What the data evaluators are really looking at is how the signal changes when you change through the different frequencies. So you're looking for phase rotation and you're looking for amplitude variations. If your flaw is getting bigger, there's going to be an amplitude change, larger. If your depth changes, you're going to get a phase change. So to show you what I mean, let's go to the 80% flaw. All of those have different phase angles. If you want me to prove it, I will. We're going to go to measure and we're going to hit peak to peak. There we got 46 degrees, 44 degrees, and 40 degrees. All right, let's do a little trial and error here. We're just going to set them exactly the same because typically you set them all to 40. So let's get precise because I know you like precise. Okay, 40, 40, 40. All right. So now we're going to go back to our cursor. So they're all at 40 degrees. Now when we go to our 80 and we measure it, you got 71 degrees, 58 degrees, 49 degrees. So this is an OD flaw, and it rotates counterclockwise with decreasing frequency. 71, lower frequency 58, lower frequency yet 49. So here we're looking at phase rotation. That's a big deal in terms of phase analysis. That's what we look for to determine depth of, at least for OD pits. Now, let's go to the 60% flat bottom hole. Let's measure that guy. Peak to peak, 103, 76, 59, counterclockwise with decreasing frequency. And we can do the same thing for the 40. It's going counterclockwise with decreasing frequency. If you want to see how that looks with a bigger window so we can look at them all at once, you know what I'm going to do just to clean this thing up a little bit? I'm just going to turn this channel off because it's distracting. All right. So here we go. 180, 60, 40, and there's a 20 in there somewhere. But we've got a certain amount of phase spread on the highest frequency, 600 kilohertz. Then we've got less phase spread with 300 kilohertz. And the least phase spread of all three of these channels is the 150 kilohertz. It's more penetrating. It can see farther out. It's good for locating tube supports because they're far away from the test coil. But you have less phase spread, so it's not as accurate when you're trying to size flaws based on their phase. So now we know that we look at phase rotation a whole lot in data evaluation. But then the next thing we look at is signal amplitude. So to show how that works, I'm going to go down to this section of the Cal standard. I'm going to zoom in on a little bit. These three wider flaws, you know, the strip charts are a measure of time or distance. So the short pits or the flat bottom holes, they have a short distance or short time. And then these wider signals are the 1 inch wide wear scars. So for this case, we know that signal amplitude tells you something about the volume of metal that's missing. So I'm going to go to, let's just see here, what am I going to do? Cursor. Let me go to channel 600 kilohertz. And I'm going to bring this down. Probably what I should do is just turn this other stuff all off so we can concentrate on one thing only. Bring this into the, trying to bring it to the center of my screen. Why is it so slow? Who knows? Now we got some big signals there. Why are they so much bigger than the flat bottom holes? Well, that's because a 1-inch wide wear scar that's 20% deep has a lot of metal missing relative to the size of the pits. So now I'm gonna make those even smaller so you can get them on the screen here. Next, I'm going to close my window size so we can zero in on a couple of these flaws. Right there, you're looking at the 20% wear scar, so 20% deep. Notice the signal amplitude. But when I go to the 40% wear scar, it's much larger. It's because there's more metal missing. Signal amplitude tells you a lot about the volume of the metal that's missing. And then if I go to the 60%er, that blows way off the screen. So because we can tell there's a definite size correlation between the amount of metal that's missing, we can use an absolute mix like this one to measure the severity of flaws. Now I have already set up a calibration curve, it's amplitude versus depth, to size these types of flaws. So if I go to that particular indication, I'm going to zoom it up a little bit so you can see a little better. Now look at the size of that. That's a 20% wear scar. And if I go measure it with a vert max, my cal curve tells me that at 1.65 volts, that's 21% deep. Watch what happens to the amplitude when I go to the 40% wear scar. It's much bigger. So now when I go to measure and hit vert max, 5 volts, so it went from 1 point something volts to 5 volts. This is reading 40%. So in summary, when you're performing data evaluation, you're not really looking so much for impedance, inductive reactance, resistance, and all that kind of stuff. You're watching for changes in phase and amplitude. End of video.